Welcome to this explainer. I am thrilled you're here. Today, we're going to follow the fascinating, literal trial-by-fire hero's journey of a copper rock. We'll be watching it transform from this dirty, impure chunk of earth into the highly refined, essential metal that absolutely powers our modern world. It's a story of intense heat, some really clever chemistry, and, honestly, dramatic transformations.
To make sense of this whole complex industrial process, we can map it out into four pretty brutal stages: concentration, roasting, smelting, and bessemerization. So let's just dive right in and see exactly how we force nature to give up its hidden treasures.
Our journey kicks off with step 1, concentration. Now, before we even think about applying any heat, we have a fundamental problem to solve. How do we separate the tiny flecks of valuable copper ore from the massive amounts of completely useless dirt and rock surrounding it? Well, the solution is the froth flotation process, and it is ingeniously simple. Finely crushed ore is suspended in this massive tank of water with just a little bit of pine oil mixed in. Then, a powerful blast of air is pumped up from the bottom, and something amazing happens. The valuable copper particles are actually wetted by the oil, not the water. Because of this neat little chemical quirk, they hitch a ride on the rising air bubbles and float right up to the top, forming this rich, skimmable froth.
But you might be wondering, what happens to the rest of the rock? While our valuable copper floats, the gangue, which is basically just the fancy metallurgical term for the heavy, unwanted dirt and earthly impurities, gets wetted by the water and just sinks straight to the bottom. To put this into perspective for you, depending on the mine, you might have to dig up hundreds of pounds of raw earth just to get a single pound of pure copper. That means an enormous volume of this useless gangue is settling at the bottom of these tanks. But by skimming that valuable froth off the top, we're left with a concentrated powder that's now roughly 25% pure copper. We've beaten the dirt, but we are far from finished.
Now that we've isolated that 25% copper powder, we move right along to step 2, roasting. Okay, in metallurgy, roasting doesn't mean popping it into an oven like a Sunday dinner, so definitely don't try this at home. Instead, roasting is a violent gas-solid reaction process. We take this newly concentrated ore and bake it at extremely high temperatures in an environment totally flooded with an excess of air. We're initiating an aggressive chemical purification designed to literally burn out specific elemental impurities before they can contaminate the final product. As that intensely hot air hits the powder, nasty impurities like arsenic and antimony react with the surrounding oxygen. They oxidize, forming arsenic trioxide and antimony trioxide, effectively burning away into the exhaust. At the same time, our primary ore, which is mostly copper sulfide, reacts with the oxygen to form copper oxide. But here's the catch. This conversion releases a very heavy, highly noticeable byproduct, sulfur dioxide gas. If you were standing anywhere near this facility, you would smell it instantly. It has this pungent, choking, almost match-strike kind of odor that serves as a very visceral reminder of the brutal chemistry transforming the rock inside. With the ore thoroughly roasted, chemically altered, and stripped of impurities like arsenic, we plunge right into step 3, smelting.
So the crucial point here is understanding how smelting differs from what we just did. It's really important to note that smelting is actually the chemical exact opposite of roasting. While roasting is an oxidizing reaction done out in the open air, smelting is a reducing reaction happening inside a tightly enclosed, oxygen-starved furnace. Here, the roasted ore is mixed with purifying, heat-generating substances like limestone and coke, which kicks off an entirely new phase of separation. Inside this enclosed inferno, chemistry takes the wheel again. Iron, which is still stubbornly mixed in with our copper, actually has a much higher affinity for oxygen than the copper does. Because of this, it forms iron oxide first. This iron oxide then reacts with the silica we've added to create what metallurgists call slag, specifically iron silicate. Think of slag as a lighter layer of liquid impurities that separates from the denser metal. Picture a pool of molten, glowing liquid rock just floating right on top of the heavier liquid copper beneath it. It is a superheated, dangerous layer that foundry workers have to carefully skim away. Once that top, lighter layer of glowing slag is successfully removed, what we have left sitting dense and heavy at the bottom of the furnace is called copper matte. This molten mass primarily contains copper sulfide and just a few lingering traces of iron. Securing this copper matte means we've successfully survived the brutal smelting phase. We've concentrated, we've roasted, we've smelted. We now enter the final dramatic chapter of our explainer, bessemerization and refining.
The molten copper matte is now transferred directly into a Bessemer converter. This thing is a massive, highly specialized, heavily reinforced steel vessel lined with refractory bricks so it can withstand unimaginable heat. The liquid matte is poured into this towering structure, mixed with sand, which acts as silica, and then blasted once again. But this time, thick iron pipes push high-pressure air right through the churning liquid metal itself.
Inside the converter, a beautifully violent three-step chemical dance takes place. First, that intense blast of oxygen converts any lingering traces of iron sulfide right into iron oxide. Second, just like in the smelting furnace, that iron oxide reacts with the sand we added to form more of that liquid iron silicate slag, which is safely skimmed off. Finally, step 3 is the grand finale. The remaining copper oxide and copper sulfide compounds are forced into close contact, and they violently react with each other. It's an incredible self-reaction, where the ore essentially tears its own bonds apart. This auto-reduction breaks the final chemical chains, yielding isolated, pure elemental copper, while blowing off the very last of the sulfur as sulfur dioxide gas. The resulting product of this multi-stage metallurgical gauntlet is known as blister copper. It earns this name because the escaping sulfur dioxide gas actually leaves a distinct blistered texture right on the metal's surface as it cools and hardens. This is a highly refined, roughly 98 to 99% pure metal. It really just needs one final polish, like electrolytic refining, to reach that perfect 100% conductive purity we require to build the circuitry and wiring in our phones, cars, and homes. However, we absolutely cannot ignore the byproduct of this incredible engineering. As our source material explicitly notes, both the roasting and bessemerization stages release massive, concentrated amounts of sulfur dioxide gas, making this technology a serious source of air pollution. So, we must end this explainer by asking ourselves a vital question. As our modern world demands more and more electronics, how do we balance the undeniable triumph of metallurgical science with the severe environmental toll required to produce the metals we rely on every single day? It's definitely something to think about the next time you plug in a device. Thanks for learning with me today.